Hey, welcome back. Twiggy here. I'm Mr. Krolak, or I call him Uncle Don's nephew. Uh, and he asked me to stand in for him today and talk to you about predictions. I know you had my cousin Floyd, a great guy, although the first time I met him, he tried to eat me. But once he figured out I was family, we're cool. So he talked to you about line regressions and statistical significance, stuff like that. So what we looked at yesterday, one of the examples was this whole thing about horizontal jumping and vertical jumping, and is there a relationship uh, or a correlation, I should say, between the two. So we put that into Desmos, and we found out we got our our line of best fit right here. Okay, and now, hey, before we go any further, let's just talk about what these values mean here. All right, so when we're talking about the slope, okay, the slope being 0.256. So what that means is if we did let's see, 2.256 over 1. Okay, that's that slope. So these would be centimeters. And the x-axis is horizontal jump, and the y-axis is vertical jump. So for every centimeter further you jump horizontally, your vertical jump improves like a quarter of a centimeter roughly. That's what that's telling you. All right. It had a pretty strong correlation. 0.88 was its Pearson correlation coefficient. And then we learned, okay, if I want to know, is this statistically significant, we figure out the degrees of freedom. So there was 15 participants. We take 2 away, that's 13. And then we look up at that critical value table, and let's say we want to be 95% confident that what we're seeing here didn't happen by accident. So in order for that to happen, we got to beat this critical value, which we clearly do, 0.88 to obviously greater than 0.514. So what that tells us as mathematicians is that there's a statistically significant correlation. All right, that means that this didn't happen by chance. Now, where we've got to be careful, and what you learned about yesterday when you watched that ice cream video, was you can't, just because there's a correlation doesn't mean there's causation. One isn't necessarily causing the other. All right, that's for the physiologists to figure out. As mathematicians or statisticians, all we can say is that the correlation didn't happen by chance. So there's always a real easy mistake to make, making a jump between the word correlation and causation. Okay. All right. All right. So I can't emphasize enough about this correlation and or causation relationship. When two variables are correlated, all right, and there's a strong relation between them, and I said this earlier, but I can't emphasize it enough, guys, is that it's tempting to say that one variable causes the other variable, but we don't know that. A correlation doesn't necessarily mean that. Okay, so the role of statistics is to test for a statistical relationship. In other words, that means a correlation. Now, if something does have a strong correlation, that could indicate that further study may yield a causal relationship between the two variables. Doesn't guarantee it, all right, but it could indicate, hey, let's I've got to bring someone else that's maybe more knowledgeable about what's actually happening here, other than the statistics part, to see is there a reason why this is related to that. All right, because I'm seeing a strong correlation between the two. All right, interpolation. So when we use the line of regression equation to make a prediction, that's called.
Sorry, get stuck in my throat. Hold on. All right, sorry about that. I just had something stuck in my throat. All right, it's all back. Okay, now, when you're making a prediction using a linear regression equation, like the one over here on the left, all right, um, that's called interpolating the data. Okay, so for example, let's say that someone didn't get to jump, okay, and they came in later. We weren't able to test their vertical jump, but we knew their horizontal jump was 196 centimeters. Okay, now that 196 centimeters is between the maximum and the minimum value of our data. Okay, I think our lowest data was probably like around 110 or something, and the highest one, the longest one, was about 260. So 196 falls between these two maximums and minimums. All right. So it's since we've got a strong correlation here, we can use this equation to make a prediction based on that. So we could say, all right, uh, if they jumped 196 centimeters, we would expect them to have a vertical jump of 44.9, about 45 centimeters. So that's using the regression equation to predict a vertical height. Now, when you set up a progression equation or a regression equation, you can predict if you're using the x and you want to make a prediction about whatever the y quantity is. Okay. However, it's not wise to do it the other way around. Even though mathematically you can, you knew the vertical jump, you could make a horizontal prediction by just substituting in the vertical for the y and solving it mathematically. But the data that we gathered and the statistical analysis that we did had the horizontal jump as the dependent variable. So if you wanted to do the prediction backwards, so to speak, you'd have to replot this and create an equation, a line of regression equation for the vertical being on the horizontal and the horizontal being on the y-axis for that prediction to be valid. Now, if you're making a prediction and the value that you're using is not between the minimum and the maximum y value, then that isn't referred to as interpolation anymore. So if we make a prediction and the x value that we're using is lower than the minimum or greater than the maximum, we don't refer to that as interpolation. It is now called extrapolation. So extrapolation is we're using a value that is smaller than the minimum or greater than the maximum when we're making a prediction. So in this case, let's say that there was somebody that jumped at 90, had a 90 centimeter horizontal jump. Well, that is below the minimum value. So the prediction that we make from that would be we would make a footnote, or you have to state that that is an extrapolation. That tells the person that is looking at that prediction that you used a number that was outside of the data set that created the line of regression equation. Okay? That's so you got interpolation and extrapolation. Extrapolation, the number you're using to make the prediction is outside the data set that you use to create the equation. All right, let's take a look at an example here. You got a score of 10 students collected on their English and their history exam, and they're shown below. A student sits for the English exam and scores a 62. Unfortunately, that student was absent on the day of the history. Use the line of best fit to predict what that student might have scored on the history exam to the nearest percent. All right. So I opened up a Desmos file, typed in, put that data into a table, and that's what we got. All right. And now we'll do our line of regression. So I go Y1, and then hit my little tilde symbol right there, tilde, and then I'm going to go M X1 plus B. Okay, and then there is my line of best fit. Okay, just to see where the centroid is, I'm going to go the mean X1, comma, mean Y1, the Y column, and label that. There it is. Okay. All right, 63.5, 9.9. All right. And then we've got our equation. All right, now we want to make a prediction. Student scored a 62, and we want to make a prediction based on this line of regression, what they get if, what we could predict they might get on the history exam. So I'm just going to let Desmos do the math for me, because the longer the decimals that we use, the more accurate our answer is going to be. So I'm just going to type in y equals m. Okay, so it's taking the m that we calculated earlier, and I'm just going to put times 62 in there, plus the b value we got, all right, which was the 29, and then right up there you can see um, what our prediction would be. So if x was 62, we would predict the history score to be a 69 to the nearest percent. All right, next example. You're given the bivariate data, that just means an x and a y data set, in a table below. What is the value of y for the mean of x? So x with the bar on the top refers to the average. That's just the notation for average. Does this require interpolation or extrapolation? So remember, interpolation means the number that you're using is between the max and the min to make your prediction. Extrapolation means the number is smaller than the minimum, or larger than the maximum. So it's outside the min and max of the data that was used to create the line. So if we're finding the mean of x, that means that the average is going to be within the max. It's going to be somewhere between the max and the min. So we're going to be using interpolation to do that. Now the process is no different. The words are just telling the reader that if you extrapolate it, your prediction might be not quite as reliable because you are using a value that's outside the data set that you use to create the line of regression equation to begin with. All right, so let's see. So I typed our data into Desmos. Okay, there it is. Got a pretty strong negative correlation going on here. Then I typed in our line of regression equation, and we got a R value of negative 0.83, so a strong negative correlation. And then there is our slope and our y-intercept. So I just made up an equation down here. Y equals m. It's using the m from our calculation. And I want to do the average of the x value right there. So I can just type in mean x1. Okay, that's the mean of the x value. It's gonna calculate those and put them in there. Okay, all right, plus b. Whoop, b. All right, so that's telling me the y value that would go to that. That's my x value, 6.5. That's the mean. I'll just show you here real quick. Mean x1 was 6.5. Okay, we could have just typed in the mean y1. Got it as well. Okay, but we did it using the prediction equation, the linear regression. All right, guys, that's it. It was nice working with you today. And thanks to my Uncle Don, Mr. Krolak, you guys. And this is Twiggy signing off.